Hi, uh, my name is Ünal Göktaş, and today I will be talking about learning PDEs with the Wolfram language. I will be giving an overview of solution methods for partial differential equations in the Wolfram language, and will discuss how these tools can be used to understand and learn PDEs by giving insight to the key ideas and algorithms supported by graphics illustrations. The talk will mainly focus on the monograph for computing symbolic solutions of PDEs in version 12.3 and on the new complete integral function in the upcoming release. So here is the outline of my talk. We will start with the simplest PDE, then continue with methods of characteristics for first-order linear equations. Next, we will go over the method of separation of variables over a fixed and temperatures problem. Then we will continue with steady-state temperatures problems. Next, we will talk on shock waves and rarefaction fan solutions. Then we will go over more applications. We will talk about the Black-Scholes equation, the spherical harmonics, and a modeling problem. Next, we will talk about the new system function, complete integral, and show an illustration of Munch cone. And this will conclude our talk. I will try to answer your questions at the end. The simplest possible PDE is u partial x equals 0, where u is a function of x and y. Its general solution is u equals C1 of y, where C1 is any function of one variable. For instance, u equals y, u equals y squared, u equals y over y plus 1, and u equals e to the power y are several solutions. Since the solutions do not depend on x, they are constant on the lines y equals c in the xy plane, where c is a constant. And for this PDE, this all returns this solution. The below manipulate shows that the solutions are constant on the y equals c curves. So we have a manipulate computation, and if we move around, we see that the solutions are constant on the y equals c curves. Consider the general first-order linear PDE initial value problem with two independent variables given as these equations here. One solution technique to solve first-order linear PDEs is the method of characteristics, where we aim to obtain an ODE initial value problem that is easier to solve than the original PDE initial value problem by a change of variables from xt to, say, s tau. Now the question is, how do you find the characteristic curves that reduce to PDE initial value problem into an ODE initial value problem? While defining the initial value problem, we require that S varies along the characteristic curves, starting at the initial curve, the line t equals 0 for this case. So S varies along these characteristics, and t varies along the initial curve, t equals 0. Tau varies along this initial curve. Hence, to uniquely define the characteristic curves in the new variables s and tau, we define the initial value problem. This is our initial value problem now. In the new coordinates system, x, 0 is mapped onto tau, 0. Therefore, the initial condition is transformed into u0 equals tau, phi of tau, to act as an initial condition for the reduced ODE in S. So by applying the chain rule and the preceding properties, we arrived at this OD initial value problem. So we arrived at an OD initial value problem, which is easier to deal with than the original PD initial value problem. Once the OD initial value problem is solved, we changed back to the original independent variables, and this method is known as the method of characteristics. I am skipping some of the details, but these details are all available in the monograph that is available in the mathematical distribution starting with 12.3 and also is available on the web. And I will be sharing that web page later on. The characteristic equations x partial s equals y and t partial s equals b are autonomous. The characteristics satisfy the OD dt over dx equals b over a. Hence, the characteristics can be solved independently of the solution u So the characteristics can be solved independent of the solution u. And note that if c equals 0 in the PD initial value problem, then u remains constant along the characteristics curves. So now we will see this method on two different examples. Let's solve the first order PD with variable coefficients. So we have this equation. This is linear and homogeneous, but has variable coefficient y. The characteristics curve satisfies dy over dx equals y, and solving this equation gives this. So u is constant on each such curve. So u is f of c, where f is an arbitrary function. Therefore, the general solution is obtained by solving y equals e to the power x times c for c. So that is, we get the solution u is f of e to the power negative x times y. And this is the same solution that we get directly from this solve. Geometrically, the solution u is constant on each characteristic curve, and here's an illustration of that. So the solution remains constant on the characteristic curves. And this is the second example. This time we have constant coefficients. And for the characteristics curves, we need to solve these OD initial value problems. We have two ODs and their conditions. And for each, we can solve by this solve. So our characteristic curves are x equals s plus tau and t equals s. So if we use this new coordinate system, we reduce the PD to the OD, and now we have an OD in S with this initial condition. And solving this initial value problem, we get that u is e to the power negative 2 times s times sine of tau. And if we replace s and tau with the original variables, we get this solution to the original problem. And this is the solution that we get directly from this whole value. This is the equivalent form of this solution over here. And if you plot, the solution looks like this. If we plot the solution at three different time values, we get these plots. And we see that as the time progresses, the wave dampens out. So in other words, the amplitude decreases. So also note that the peaks at the various times move slightly to the right. Now let us go over the method of separation of variables over a fixed and temperature problem. Suppose that we have a rod with length L, whose lateral sides are wrapped with insulation. And if this rod is placed in an environment whose temperature is fixed at the same temperature, at some temperature T0, after a sufficient time, the temperature of the entire rod stabilizes and comes to a steady state temperature. So we have a rod, and the left-hand side is held at temperature T1. The right-hand side is held at temperature T2. And this is the temperature, T0 is the temperature when we started yes. The basic PDE that is modeling the one-dimensional heat flow is this equation. Since the temperature U was fixed for all times t greater than 0 at T1 and T2 at the two endpoints, x equals 0 and x equals L, we have these boundary conditions. So when x equals 0, we have T1, and when x equals L, on the right-hand side, we have temperature T2. Since we started monitoring the rod temperature from the time rod reaches a temperature of T0, we have this initial condition. Hence, the PDE, boundary conditions, and the initial condition make up the initial value boundary value problem. Let us first suppose that T1 and T2 equals 0. And also assume that, so now we are solving this problem, and also assume that the solution can be written as x of x times t of t. In other words, we assume that the solution is separable. So if we substitute this form to the PDE, we get this. And if we divide both sides by k times x times t, we get this. So we now have two ODs, one for t and one for x. And for t, the solution is this, and for x, the solution is this, when lambda is greater than 0. So the next step is we impose boundary conditions. So when we require x of 0 equals 0 and x of L equals 0, we get that A equals 0, and we find that when lambda n equals p times n over L square, this term will be 0, so we have a non-trivial B here, which is non-zero. So there are infinitely many solutions of the PDE such that UN equals this. So since the equation is linear, we can use the superposition principle, and we can write the solution as a summation, infinite summation this time, because we have infinitely many solutions of this type. The next step is we impose the initial condition, and the lambda n's are called eigenvalues. These functions are called eigenfunctions. And using the orthogonality of the eigenfunctions and using the result of this integral, we find that Bn equals this. Here's the Bn. So if we substitute this Bn into the summation, we get this solution for U. And this is the same solution that this whole value returns over here. The method outline is so-called separation of variables method, and also called the eigenfunction expansion method. So now let us return to the fixed end temperature problem. For this initial value boundary value problem, the solid value problem returns this. So now, in addition to the infinite summation, we have this term. For specific values of k, l, and t0, t1, t2, we find this solution. And if we plot the solution, we get a plot like this. Here is this whole truncated solution function is a simple function that we define like this in order to truncate the infinite summation at a desired point, so that we get sufficiently good approximation for the infinite summation. Okay, so now the next is suppose that U represent temperature after a sufficiently long time under the same environment and conditions. Experiences show that the variation of temperature with time dies away, as we expect that the limit of U as t tends to infinity exists and depends only on x. So we have the limit just in terms of v of x. V has to satisfy the boundary conditions and the heat equation. So if we solve this OD problem, we get this for V. So this is the limit of the solution of the preceding initial value boundary value problem as t goes to infinity. So for specific values, if we solve the fixed end problem and steady state problem, and this manipulate shows nicely that for larger values of time, we get close to the steady state solution. So this is the steady state solution line here. Okay, the next topic is we have an initial value problem in which the initial data is formed of two constant states, UL and UR, and we have a jump discontinuity at x equals 0, and this is called Riemann problem. So let's consider the Berger's equation with the Riemann problem. So we have this, and this is our initial condition. So when UL is greater than UR, we have a weak solution of the form of a shock wave. And when UL is less than UR, then we have a rarefaction fan solution. So let's see this on this example. We have this initial condition, and now we have this solution. And if you plot, we see that this is a weak solution. And if we change the initial condition, then we get a rarefaction fan solution. So this is the solution, how it will look like when we have a rarefaction fan solution. Okay, let's see now the generalized Berger's equation. Now we have epsilon here, and if we solve this, we get this solution. And the solution is smooth for any positive values of epsilon. But the solution develops a shock discontinuity in the limit when epsilon approaches to 0. So if you plot the solution for smaller values of epsilon, we see that we are building a discontinuity here. Okay, this is an application from finance. So Black-Scholes equation applied to European options. So this is the equation this is the PDE that we will be solving. So here, V is the value of the option with underlying asset S and elapsed time T. R is the interest rate. Q is the dividend yield. Sigma is the volatility or annualized standard deviation of the asset price. If K is the strike and T is the time of maturity, the initial condition for the put option is given like this. So for the put option problem, this all returns this solution. So if we compute the value of an option for typical values of parameters like this, and if we substitute these parameter values into the solution that this all value found, we get this value. And if we compare this value given by financial derivative, we see that we get the same result. Now, if we repeat the same for the call option this time, we get this solution from this all value. And if we compute the value for typical values of parameters again, and compare with the result from financial derivative, we see that the results are same. Okay, I will skip this, and I want to talk about complete integral. As Devendra already mentioned, we have a new function now, complete integral, and complete integral of a first-order partial differential equation in n variables is a solution that depends on n arbitrary constants. So I will skip also this envelope example, and I want to show you an example that has the Munch cone. So suppose that we found the complete integral of this partial differential equation. So we have two families of complete integrals, and if we plot these, we get this type of plot. Okay. All the tangent planes to possible integral surfaces through a point P form a family of planes enveloping a conical surface, which is called Munch cone, or elementary cone at the point P with P as its vertex. In other words, the problem of solving the original PD is to find surfaces which touch the Munch cone at each point along a generator. So now let's illustrate this property. So we just take one branch of the complete integral. We define the tangent plane. So now we fix W equals W0. This restricts two parameters C1, C2 by implying a dependence. So this is the implicit tangent plane. And now we define the cone surface. And we see that this is a genuine quadratic. So this is the solution surface through point x0, y0, and z0. And if we use manipulate, we get this nice Munch cone property. So this is a nice application of complete integral. Okay, so I have skipped many of the details due to time constraint, but as you probably already know, starting with 12.3, we have a new monograph for symbolic solutions of PDEs, which is also available on web page. So this monograph has lots of examples details, applications, plots. So I hope you enjoy this monograph and use it. So today, this is all I have. Thanks for attending.
Thanks, Unal. Does anybody have any chat or any questions for Unal? You can put them in the Pathable chat, or because those stay around, and then he can answer them for you. And Unal, does your group, or do you have any office hours in the tech conference, or I don't remember if you did.
Yeah, yeah, we have an office hour. Yes.
Okay.
Yeah.
So yeah, if anybody has other questions that they think of later, they can. I think all the groups have like chats there. You can put in a question or connect with them live during their office hours.
Okay.
All right. If nobody has any questions, just give it a minute to see if anybody types anything. We can end the meeting then. And
and I skipped some of the pages on the presentation. The presentation is available on Pathable. So.
Oh, good point. Yeah, you already uploaded the files to the talk page in the files tab. I'm not seeing any questions that anybody else came up with. And there's none in the Zoom chat. So I think we'll end it here unless anybody has anything else. Thanks everybody for coming. Thanks, Unal.
Thanks.